Have you ever just stared at a screen full of static, that pure random chaos, and wondered if anything could possibly come from it? Well, what if I told you an AI can look at that exact same noise and pull out a stunning photorealistic image? It sounds like actual magic, but it's not. It's this brilliant process of, reverse engineering reality. And today, we're going to pull back the curtain and see exactly how it works. So that really is the big question, right? How in the world do you create a masterpiece from nothing but pure static? I mean, it feels like trying to sculpt a statue out of thin air. But here's the secret. It's not about creating something from nothing. It's actually about finding the image that was already hidden in the chaos the whole time. Just look at this, seriously. On the left, you've got that total static, completely meaningless, and on the right, you've got this whole grid of incredibly detailed images, cars, animals, ships, all of them generated by an AI that started with nothing more than that noise. This incredible transformation is all thanks to something called a Denoising diffusion probabilistic model. Yeah, it's a mouthful, so let's just call them diffusion models. Now, at the core of all this is the bigger idea of generative AI. See, most of us are used to AIs that analyze stuff. They recognize your face in a photo or tell you there's a cat in a video. But generative AI, it's a whole different ballgame. It doesn't just analyze things, it creates them. It learns the deep down patterns of what makes something, that thing, and then it can spit out brand new examples that have never existed before. Honestly, the best way to get your head around this whole thing is with an analogy. So don't think of the AI as a painter with a blank canvas. Instead, picture the AI as a sculptor. And it's been handed this giant, messy block of marble. That block of marble is the random noise. The AI's job is to very carefully chip away at all that noise, piece by piece, to reveal the perfect image it knows is hiding deep down inside. Okay, so before our AI can become this master sculptor, it first has to really understand the block of marble. It has to learn how a perfect, pristine image turns into noise in the first place. This is what we call the forward process. And it's basically a masterclass in how to systematically and beautifully destroy an image. So here's how that works. The AI is shown millions and millions of high-quality images. Then, for every single image, it starts what's called the diffusion process. In this long sequence, maybe 1,000 tiny controlled steps, it adds just a little bit of what's called Gaussian noise, which is really just a specific, predictable kind of randomness. It's the slow, methodical process of taking something perfect and making it chaotic. And you can see that exact process happening right here. A crystal clear picture is slowly, step by step, getting corrupted as more and more noise gets layered on top. After about 1,000 steps, poof. The original image is completely gone, totally lost in a sea of static. But here's the crucial part. The AI is watching this entire process of destruction, carefully learning how the noise gets added at every single step along the way. All right, now for the fun part, the reverse process. This is where the real magic happens. So after watching countless images get turned into pure noise, the AI's actual training can finally begin. It is time to teach it how to be that sculptor and reverse all of that damage we just did. So what exactly is the AI trying to do? Well, its goal is surprisingly specific and actually pretty simple. We give the AI a noisy image from any of those 1,000 steps, and its one and only job is to predict the exact noise that was added to get it to that point. It's not trying to guess the final image, it's just trying to identify the static. It becomes this highly specialized noise prediction machine. The whole training loop is like this simple 4-step dance. Step 1, we start with a real image. Step 2, we jump to some random point in that 1,000-step destruction process and add the right amount of noise. Step 3, we show this messed up image to our neural network and ask it, hey, what noise did I just add? And finally, step 4, we compare the AI's guess to the actual noise we used. If it's wrong, we just tweak the network a tiny bit to get it closer next time. And we do this millions and millions and millions of times. And this, right here, this is the beautiful payoff from all of that training. To create a brand new image, we don't start with a real one at all. We just give the AI a block of pure random noise. Then, over 1,000 steps, the AI predicts the noise in the image, and then it subtracts just a little bit of it. And as it keeps chipping away, step by step, a coherent, complex, and often photorealistic image just emerges from the static. It is quite literally sculpting with noise. Okay, so the theory is super elegant for sure, but the real test, the proof, is in the pudding, right? So just how good are the images that these diffusion models can actually make?
Take a look at these. These are samples generated after the model was trained on a whole data set of church pictures. Just look at the complexity of the architecture, the different styles, the way the light hits. It's incredible. The model hasn't just memorized pictures of churches. It's learned the deep structural patterns of what makes something a church, and now it can invent entirely new ones out of thin air. And what's amazing is how versatile this is. Here are some generated images from a bedroom dataset. And again, just notice the insane variation. Different furniture, all kinds of decor, even different camera angles. Every single one is completely unique, but every single one is also, without a doubt, a bedroom. But we don't just have to use our own eyes. We can actually measure image quality with a metric called the FID score. Basically, it compares how realistic the AI's images are to a set of real ones. And with FID, lower is better. So when this research first came out, on the standard SciFar 10 benchmark, this diffusion model got a score of 3.17. Now, that number, 3.17, might not mean much by itself, but oh man, when you put it in context, it is a huge deal. This table here compares its performance to other top models at the time. Look at that. It didn't just beat models like SNGN or NCSN, it absolutely left them in the dust. It even managed to squeak past the legendary StyleGAN 2, which was the reigning champ. This wasn't just a small improvement. This was a state-of-the-art result that put diffusion models squarely on the map. But here's the thing. This technology is about so much more than just making cool pictures. The way these models work, this whole process of finding a signal inside of noise, it has these really profound implications for how AI understands and thinks about complex data. So by learning that path from pure noise all the way to a clear image, the model builds this kind of internal map of ideas. We call it a latent space. And on this map, similar concepts are located close to each other. This opens up all these incredible creative doors. For instance, you could find the point on the map for a red car and the point for a blue truck, and then you could ask the model, hey, what's halfway between these two? And it'll generate a totally logical, seamless blend of the two ideas. Okay, now this is where things get really fascinating. The researchers looked into how the model uses its brain power, its bits of information, to rebuild an image. And what they found was that over half of the data, 55%, is spent describing these tiny, almost imperceptible details. The broad strokes of the image, the stuff we notice first, that's only 45%. This tells us the model is ridiculously good at seeing details that are practically invisible to us. And that discovery points to a really surprising but powerful side hustle for this tech: data compression. Because the model builds images step by step, starting with the big picture and then filling in the details, it automatically acts as a super effective form of what's called progressive lossy compression. It's like it has its own built-in, super intelligent JPEG algorithm that knows how to prioritize the most important visual information first. So there you have it. We've gone from a screen of pure static to a photorealistic image, not by creating something from scratch, but by teaching an AI to find the signal that was hiding inside the noise all along. And that leaves us with a really provocative final thought. We have successfully taught an artificial intelligence how to find complex, meaningful, even beautiful patterns inside what, to our human eyes, just looks like random chaos. So the question is, what else can it learn to see that we can't?